Okay, these are the class activities for lesson number 3. I have a system of linear equations, and I want to set up an augmented matrix that represents the system. So I put in my x coefficients in column 1, 0 and a 1. My y coefficients in column 2, 1 and -3. My z coefficients in column 3, -2 and 4. And then I augment the coefficients with the constants that are on the other side of the equal sign. All right, and now I'm supposed to use row operations to put the matrix into reduced echelon form. So I want my main diagonal to be 1s, and I want to have 0s above and below my main diagonal. Okay, so that 0 in the first entry is problematic. I would like that to be a 1. So one of the easiest row operations is to just swap 2 rows. So that's going to be my first move here. I'm just going to swap row 1 and row 2. So I have 1, -3, 4, -6, and 0, 1, -2, 3. So now I have a 1 as my leading entry in the first row, and I have 0 below it. So that first column is done. I have a 1 with a 0 below it. Move to the next column as I move to the right. I have a 1 as the leading entry. That's great, and there's nothing to knock out below it. So I already have this in echelon form. This is triangular form. My main diagonal is 1s, and I have 0s below the main diagonal. But now I need to work right to left. I want to have 0s above the pivot positions that I have identified, the 1 and the 1. So I need to knock out that -3 that's above the 1. So row 1 needs to change. Row 1 is going to become row 1 plus 3 row 2. Okay, so row 2 is not changing, so I'm just going to copy that down before I do anything. Okay, row 1 is changing, and it becomes row 1 plus 3 row 2. So row 1 in the first entry, I have a 1. 3 times row 2, that's 3 times 0. So 1 plus 3 times 0 is still 1. And then -3 plus 3 is 0. And 4 plus -6 is -2. And -6 plus 9 is 3. This is now in reduced echelon form. So I have my main diagonal is 1s with 0s above and below the pivot positions. So circle the pivot positions. Those are my 1s there. And the variables that correspond to pivot positions are called basic variables. So I have a pivot in column 1. Column 1 corresponds to the x variable. So x is a basic variable. And then column 2 corresponds to y, and I have a pivot in column 2. So y is a basic variable. Now column 3 does not have a pivot, and column 3 corresponds to the variable z. So z we call a free variable in this system. So I want to write the system of equations that corresponds to the last matrix in B. So I have x minus 2z equals 3. That was my first row. And my second row says y minus 2z equals 3. Okay, so the convention is that when we write the general solution to this system, is that we rewrite each basic variable in terms of the free variables and or the constants. And then we just list which variables are free. And again, this is a convention, right? You could solve for any variable, but we've decided that we're going to solve for the free variables in terms of we're going to solve for the basic variables in terms of the free variables. So z is my free variable. So next to z, I just write free. And then I'm going to solve for x and y in terms of z. So x is going to be 2z plus 3, just adding 2z to both sides here. And y, add 2z to both sides, and I get the same thing, 2z plus 3. So to give 2 specific solutions to this system, because there are infinitely many, two specific solutions, you can find them by choosing a value for z. Z is free, so you get to pick it. So I'm going to pick 1 for z. That means that y and x would both be 5 when you replace the z in their formulas with a 1. Right? Another specific solution, if I pick z to be 0, then x and y will both be 3. Okay, here's another one. This is a larger system. I have 5 unknowns and 4 equations. So I just want to solve it using Gaussian elimination, which is row reducing the forward phase and the backward phase. Okay, so my x1 coefficients are 1, 0, 0, 1. My x2 coefficients are 0, 1, 0, 0. My x3 coefficients are -2, 0, 1, 2. x4 coefficients are -3, 2, 1, 1. x5 coefficients are -5, 3, 2, 3. And then I augment with the constants, 2, 2, -1, -2. Okay, so to solve this, I'm going to start by working column by column, left to right, where I want to have 1s on the main diagonal and 0s below them. So it's really already worked out real nicely that my main diagonal, my upper left to lower right main diagonal, already has all 1s on it. So that's really helpful. Now I just want to knock out everything below that main diagonal. I want to have only 0s. I'm going to do it from left to right. So the first goal is to get rid of this 1 down here. So that means I'm just going to do row 4. Sorry, it's row 4. That needs to change. So row 4 is going to become row 4 plus negative row 1. So my new matrix, nothing changes except row 4. So it's helpful to just rewrite the other 3 rows before you even start. Okay, row 4 is going to become row 4 minus row 1. So 1 minus 1 is 0. 0 minus 0 is 0. 2 minus -2 is 4. 1 minus -3 is 4. 3 minus -5 is 8. And -2 minus 2 is -4. Okay, column 1 is done. I have a 1 with 0s underneath it. Column 2 is done. I have a 1 in the pivot position with 0s underneath it. Okay, column 3, I have a 1 in the 3rd row, so I want to knock out that 4 that's beneath it. So I'm going to do row 4 is what needs to change. So row 4 plus -4 row 3. I'm working on column 3, so I use row 3 to knock out everything below row 3. So this is row 4 plus -4 row 3. Okay, so my new matrix, only thing that's changing is row 4, so I'm just going to copy my other rows real quick. 1, 0, -2, -3, 2, 0, 1, 0, 2, 3, 2, 0, 0, 1, 1, 2, -1. And then row 4 is changing. It's going to become itself -4 row 3. So that would be 0, 0. And then 4 plus -4 is 0. 4 plus -4 is 0. 8 plus -8 is 0. And -4 plus 4 is 0. Get a row of zeros. Okay, so column 1, column 2, and column 3 are all done in the forward phase. And then column 4, I would like to have a 1 in that main diagonal position, but there's no way to make a 1 there because I just have all zeros. So I am done with the forward phase. I've done everything I can. I found all my pivots. My pivots are here and here and here. The leading entry of each row is a pivot. My fourth row doesn't have a pivot because it doesn't have a leading entry. It's all zeros. So my next step is to work backwards from right to left, and I want to eliminate everything above the pivots. So in column 3, I have a pivot, so I want to eliminate everything above it. I want to eliminate that -2. So row 1 needs to change. It's going to become row 1 plus 2 row 3. And so only row 1 is changing, so I'm going to copy everything else. Okay, so row 1 is going to become itself plus 2 row 3. So 1 plus 2 times 0 is still 1. 0 plus 2 times 1 is 2. -2. Oh, I used the wrong row. Row 1 plus 2 row 3. So row 1 is 1 plus 2 times 0 is 1. 0 plus 2 times 0 is 0. -2 plus 2 times 1 is 0. And then -3 plus 2 times 1 is -1. -5 plus 2 times 2 is -1. And 2 plus 2 times -1 is 0. Okay, that is your reduced echelon form. I have 1s on the main diagonal and 0s below and above them. So 0s below and above every pivot. Okay, so now what I do is I translate this back to equations. I'm just highlighting my pivots because those are my basic variables. So this says x1 minus x4 minus x5 is 0. x2 plus 2x4 plus 3x5 is 2. And x3 plus x4 plus 2x5 is -1. And now I'm going to solve each of these equations for the basic variable in terms of the free variables, right? So my free variables are the variables that correspond to non-pivot columns. So x4 and x5 are free. So I solve each of these equations for the basic in terms of the free. So x1 is x4 plus x5. x2 is -2x4 minus 3x5. And x3 is -x4 minus 2x5 with x4 and x5 free variables. So that is my general solution to the system. I messed up just a teeny bit when I was solving for x2 and x3. I forgot that there were constants on the right-hand side. So this is 2 minus and -1 minus. Okay, one more. There's just, yeah, 2 more. Use Gaussian elimination to find the general solution to the system. So first we translate to a matrix. So I have 0, -2, 1, -3, 5, -2, -6, 16, -7, augmented with 1, -1, 1. Okay, so I'm going to do a row swap to get a 1 in the first row, first column. I'm going to swap row 1 and row 3. So I have 1, -2, -7, 1, -2, 5, 16, -1, and 0, -3, -6, 1. Okay, so now I work left to right, column by column. I want to eliminate everything under this 1. That's my first pivot position. I want zeros underneath it. So I am going to change row 2. It's going to become row 2 plus 2 row 1. So the only thing changing is row 2, so I'm going to copy row 1 and row 3. Okay, and row 2 becomes row 2 plus 2 row 1. So I get 0. Okay, so 2 times -2 is -4, plus 5 is 1. 2 times -7 is -14, plus 16 is 2. And 2 times 1 is 2, plus -1 is 1. Okay, so column 1 is set. I have a 1 in the first entry of the column with zeros underneath. Column 2, I have a 1 on the main diagonal, right? But I want zeros underneath it. So I'm going to change row 3. So row 3 is going to become itself plus 3 row 2. So only row 3 is changing, so I'm going to copy row 1 and row 2. Okay, so row 3 is going to become itself plus 3 times row 2. So I get 0, 0. 3 times 2 is 6, plus -6 is 0. And 3 times 1 is 3. 3 plus 1 is 4. Okay, so I can stop now, even though this is not in reduced echelon form. This last row tells me that the system is inconsistent, because that says 0x, was this x, y, and z? Yeah, 0x plus 0y plus 0z equals 4, which says 0 equals 4, which is impossible. So we say this system is inconsistent. It has no solutions. There are no values of x, y, and z that can make all 3 equations true at the same time. Okay, one more. Choose an h and a k such that the system has no solution, a unique solution, and many solutions. Separate answers for each part. Okay, so translate this to a matrix, and I have 1, 2, -3, h, and 1, k. So I want to put this into echelon form. So I'm going to knock out this 2 using the 1 above it. So row 2 is become row 2 minus 2 row 1. Row 1 doesn't change. I'm just copying it. Okay, row 2 is going to change. It's itself plus -2 row 1. So I get 0. -2 times -3 is 6. So I get 6 plus h in the next entry. And then -2 times 1 is -2 plus k. -2 plus k. Okay, what determines whether this system has no solutions or solutions? we'll talk about unique and many in a minute. But what makes something have no solutions is when this row says 0 equals 0, right? So if 6 plus h and -2 plus k are both, 0 equals a non-zero number. That's when you have no solutions, because 0 equals a non-zero number is just not true. So for no solutions, we would have no solutions if 6 plus h equaled 0 and -2 plus k is not 0. Anything other than 0 would make 0 equal a number, and we would have no solutions. So that happens when h equals -6 and k is anything other than 2. So that would give me no solutions. Infinite solutions, or many solutions, happen when you get 0 equals 0, right? So 0 equals 0 in that last row. That would give you many solutions. So that happens if 6 plus h is 0 and -2 plus k is 0. So h is -6 and k is 2. So that's the many solutions. A unique solution would be if 6 plus h was not 0, and -2 plus k can be anything. Doesn't matter, because if the left-hand side of the equation isn't 0, then you can solve. So unique solution, that happens when 6 plus h is not 0. So h is anything except -6.